Hello. This is a video on how to show the calculations for an ideal gas law problem. I will not explain to you the ideal gas condition. It was already explained in previous videos. If you if you've watched other videos on how to do gas problems, you don't need to. You can fast forward through the pod on how to do gas problem steps, which I'm going to talk about right now. Okay. If you haven't, for any gas problem, um, you should have you should have already watched the video on the overview of gas problems, where I explain how you actually go about figuring out what mathematical relationship you want to use for gas problems, because there's several. And there are basically two questions you ask yourself to figure out the correct math equation. What this is this is a step that steps that one follows to do any gas problem. Okay. So the first question you ask yourself is how many conditions are there in the problem? Now, conditions I define for me as if I do something to the balloon or the gas container and I see action verbs, I have what I call the two condition problem. And the first condition would be the gas as it originally was. It has a volume, it has a temperature, it has a number of moles, it has a pressure. And those would all have subscript 1 indicating the initial condition. Then whatever I do to it, I cool it, I heat it, I compress it, it leaks. Then you have a new condition, which I call condition 2, which would be pressure 2, volume 2, temperature 2, number of moles 2. And you can again see if you have a two condition problem, if there's action verbs. Or if there are no action verbs, what you're really doing is you say you have a gas and you're describing that gas. And I call that a one condition problem. Okay? If you have a two condition problem, then there's another set of questions you have to ask about what's being held constant and what's changing. Now, for this one, the ideal gas law, you don't have a two condition problem. You actually, you only have one condition, which does not require you to ask, well, you kind of do, but it's not to figure out the different types of mathematical relationships. It's to be able to manipulate the one mathematical equation that you have. So for one condition problem, you are always going to have the equation PV is equal to nRT. Okay, but you need to then get X, the variable you're looking for, on one side and everybody else on the other side. Okay, once you have that equation, now I'm kind of flipping 3 and 4. Okay, 4 basically asks you, hey, get the right mathematical equation, and 3 is write down what you know, what you're looking for, and in essence declare your variables. You can do either one of them first, but you must do both of them first before you go 5, 6, and 7. Basically says, hey, now plug in units are canceling because you declared the variables that way. And give me the answer with the right unit of significant figures. Okay, so let me go to the problem. This problem, actually, I created this page before I wrote the ideal gas law calculation -1 problem handout. So you would see it, the question, as a wiki page, which it doesn't make a difference. It's the same exact information. I just did this on a piece of paper. So if you look at the question, you can see that there is no action verb. Contain is not really an action verb. So there's no decreasing, depressing, no cooling or heating. So what you have is you only have one condition. So basically you have a ballooning describing it. And whenever you have a one condition problem, you use the ideal gas law, okay, which is PV is equal to nRT. So now, with all ideal gas laws, you have this thing called R, which is the gas constant. It is a constant, and a constant never changes. That's why it's called constant. So the rule is you have to take all the other variables and change it into the units of R. Okay? You must. Okay? You will get, like when you did temperature, where if you don't do temperature in K, right here, you get absolutely no credit. Same thing with the ideal gas law. If your ideal gas law, you don't use this constant, and you don't change your variables into the units of K, you get no unit. You get no credit at all, no partial credit. Okay. So therefore, no matter what they give you in the question, you better change your units of pressure into atmosphere, temperature into K, which you didn't do anyway, and then your N as moles. Okay, so as you can see from the question, the volume you're looking for. So if you knew the volume, you better have the volume in liters. But here you're looking for the volume in liters. Okay, so you also have 2.05 moles, and you have a pressure of 452 millimeters of mercury and 21 degrees C. So you need to change the degree C into K, which I did, and you need to change the 452 millimeters of mercury into atmospheres. Well, how do I know this relationship? I already gave you a handout of a string of pressures in different units of pressure. So they're all equivalent to each other. That's why the equal signs are there. So that's all your conversion factors. So you stack them up on top of each other. Put no unit that you want to get rid of on the bottom. Put the unit on the top. Okay. You do not have to memorize pressure units. You'll be given that string whenever you need them. Okay. So therefore, there's 760 millimeters of mercury in one atmosphere to give you a 0.595 atmospheres. And as you do with all of these conversion factors in your declaring the variable, I came in with 3 significant figures. I'm coming out with 3 significant figures. No rounding. Okay? So now you have all the variables, and you have R. Okay? There are more ideal gas constant values, but the units are different too. Okay? To make our life simple, we will only use this one. Okay, period. You cannot use a different one. Okay, and some people don't use a 1 here; they use an 0.6. But I'm just reducing them to significant figures for you. So if you look at another book, it would be 0.08206 or some number like that. But I use 1. And as long as we're using the same number, okay. So PV is equal to nRT. Okay, you don't need little subscripts because there's only one condition. Okay, and you only have one gas, so therefore you don't need to put subscripts. But you do need to get the right mathematical equation. This is not the right equation to get x on one side and all the other variables on the other side. Okay, that becomes volume is equal to nRT over P. Okay, that is your correct equation. Since you have declared all your variables and put all your units into R's units, so N, R, and T over P. So you can see the atmospheres cancel, the K's cancel, the moles cancel, and you should get the units of L, which that's what you're looking for. Okay, and so volume is equal to so many liters, and then you put into 3 significant figures. Okay. Now let's say you want it in milliliters. You don't change. So you don't change the constant. You just get into liters, and then you change the liters into milliliters at this point. Okay. So the that's how you do an ideal gas law problem. Just one thing about the theory or the theory. I teach most chemistry teachers teach the gas laws, which is a two-condition problem first, and then the ideal gas law. Okay. Actually, what happens is you have the ideal gas law, and the two-condition problems are just two ideal gas laws stuck on top of each other. So technically, you could take PV is equal to nRT and put little ones here and divide it all and put the same exact variables on the bottom and put little p2s and cancel out the things that aren't changing, and you would end up with all the gas laws. Okay, but it makes it's a little easier to explain and to go through the first time by doing the gas laws first, the two condition problems, before doing the one condition problem. Okay, so that's how you do an ideal gas calculation. The big thing again is you are going to use one R value only, and you need to take all the units that you have and put it into the units of R. Thank you.